A manufacturer of paper products wants to compare the variation in daily production levels at two paper mills. Independent random samples of days are selected from each mill, and the production levels in units are recorded. The data are shown in the table on the web page and also in an Excel file. Do these data provide sufficient evidence to indicate a difference in the variability of the production levels at the mills? Use alpha equal to 0.05. Okay, this is a test to determine if there's a difference in the variability. Variation, of course, is measured by standard deviation and also variance. And what we're going to do is look at that variability and measure it in terms of variance. So I'm going to let population 1 be the production levels from mill 1 and population 2 be the production levels from mill 2. Also, I'm going to let sigma sub 1 squared be the square of the standard deviation from the first sample, or it's the variance of the production levels in mill 1. Sigma sub 2 squared is the square of the standard deviation of the data in the second sample from mill 2, and the square is the variance. And what we want to do is to test to see if we can determine there's a difference in this variance. Well, to test to determine if there's a difference, what will we assume? We'll assume that there is no difference. So we're going to assume that sigma 1 squared is equal to sigma 2 squared. And if we have the evidence from the samples, strong enough evidence to reject that, we can conclude that they are not the same, that there is a difference. So our alternative hypothesis is sigma 1 squared not equal to sigma 2 squared. The next step in a hypothesis test is to look at the sampling distribution. And the sampling distribution for testing of variances, we are not going to use the normal or the t-distribution. It's actually what's called an f-distribution. Since alpha is equal to 0.05 in this problem, and it is a two-tailed test because of the equal to not equal to, I'm going to split alpha for both ends of the distribution. So alpha over 2, the upper area, is 0.025, and also the lower end is 0.025. Now this presents somewhat of a problem in the sense that with the normal distribution and the t-distributions, they were symmetric. So whatever critical value you had for the upper end, there was an opposite negative critical value for the lower end. Here, the upper end critical value will be different than the lower end. They're both positive and they'll be different numbers. Now, as it says in the textbook, this distribution is the set of quotients of the sample variances from population 1 and population 2. If I look at my sample variance from population 1, I'm going to go to the data set and calculate the variance on that. I get 51.564. And again, that's an estimate of the sigma 1 squared. S2 squared, the sample variance from population 2, I calculated at 28.015, and that is an estimate of sigma 2 squared. Now, the distribution is a distribution of the quotients of these variances. So if we looked at all of the samples that we could possibly take from population 1 and population 2 and calculated the variances on those samples and took the quotients, those quotients would make up what's called the f-distribution. If the null hypothesis is true, that sigma 1 squared is equal to sigma 2 squared, then our quotients of these sample variances, should cluster around 1. So really, the quote-unquote center of this F distribution is 1. If the null is true, then this quotient of these sample variances should be pretty close to 1 in the quote-unquote center of this F distribution. Now, if the population variances are not equal, then the quotient will move away from 1. The quotient of the sample variances will move away from 1. If the sample variance in the numerator is larger, then that quotient will move to the right of the center in the distribution. If the denominator is larger, then it will move to the left. Now, we just took one sample from population 1 and one sample from population 2. And it turned out that S1 squared is larger than S2 squared. So to measure their difference, this is going to be an upper end test. As a matter of fact, you can always make it an upper end test on the distribution if you simply allow population 1 to be the population that has the larger sample variance. That way, when you run the test, that test statistic will move to the right of center and go out to the right. And then you can always use one critical value, the upper end critical value, to determine the result of the test. For now, I'm going to call that upper end critical value F sub alpha over 2, or F sub 0.025. Now, step 3 is the rejection rule. I'm going to reject H sub 0 if my test statistic, which I'll calculate in a moment, is greater than my critical value. Now, in step 4, that's where I calculate the test statistic. And the test statistic is simply the quotient of the sample variances. So I got S1 squared over S2 squared. So I've got 51.564 divided by 28.015. And on my calculator, that comes out to be 1.84. Now I'm going to go ahead and go back here for a minute and get my critical value. And I'm going to use the F distribution table in the back of the book. There's really 3 numbers that you need to get the F critical value. You need the numerator degrees of freedom, and the numerator degrees of freedom is just the sample size you use to get that variance from population 1, subtract 1. And in our case, our sample size was 11, so 11 subtract 1 is 10. And for population 2, our sample size was 17, so I'm going to subtract 1 from the 17 to get 16. Also, I have an upper tail area of 0.025. So if I go to the F distribution table, I'm going to look down to row 16, the denominator degrees of freedom, across to column 10, the numerator degrees of freedom, and then within that group of values, I'm going to select the area in the upper tail at 0.05. That leads me to 2.99 as my critical value. So the F distribution table works a little different than the standard normal table or the T distribution table. You have to look up what's called the numerator degrees of freedom, the denominator degrees of freedom, and get an upper tail area. And since this is a two-tailed test, I split alpha, so my upper tail area is 0.025. Now we want to go ahead and with step 5, now that we have the test statistic and critical value, draw some sort of conclusion. And I'm going to conclude to do not reject H sub 0, since 1.84 is less than 2.99. So my quotient of sample variances, is too close to the 1. The ratio is too close to the 1. It's not far enough away. My 1.84 is below the 2.99, and I'm not going to reject. So the answer to the question, which is, do these data provide sufficient evidence to indicate a difference in the variability of production levels at the paper mills? The answer is no. The data does not provide sufficient evidence that the variability of production levels is different between the two mills. Now you can also run this test using a p-value, and I've provided some instructions on how to calculate that. One way the book demonstrates is by using the F table, and I show you on the web page how that goes. And a better way actually is to use Excel, and there's two options in Excel that you can use to get that p-value. And remember, the Excel will be available for you when you're taking the exam. Again, also remember that there's two ways to run hypothesis test. One in which we compare a test statistic to a critical value, and that's what I've done here in the video. Another way is to compare the p-value to the level of significance alpha. Both of those will always agree, and you should know how to do them, each one.